well, off we go then. Good morning, gentlemen. I am doing this at Shem's request, really. It was set out as a tutorial, if you like, to try and explain to you the technology behind the development of Concorde, and perhaps to use that to illustrate some of the difficulties in developing supersonic transports, which you as graduates might meet when you get out into the wide world. I know from what Shem has said that there are several aerospace professionals logging into this, and if the students will just bear with me for a minute, I'd just like to say to those guys that this presentation was prepared for students. I haven't had time to change it. Late in the day, I decided that it might be a good idea to use or make some comments really on the current batch of supersonic projects which are going around, and to use those comments also as an illustration of the sort of problems you can expect to run into. So I should say there that anything I know about those projects is entirely what I obtained from published data, supplemented by my own experience, or if you like, my own prejudices. But anyway, here we go. Okay. Okay. Now this one really is my favorite picture of Concorde, which says it all, but it was only really meant to go up there as a sort of introduction. What I'm going to talk about is the configuration development. Hi, Don. Is the configuration development we went through, and how we went about drag reduction. Some remarks on trim drag and center of gravity control. Some rather important ones on power plant development and the engine inlet matching. Some bits on the intake control. Then I'm going to move to some possible constraints on future supersonic developments and make some remarks about boom, spike, and Aeron. Why did we choose Mach 2 in the first place, you might ask? Well, this is a generalized picture of specific range against Mach number, and you can see that when you do get supersonic, this region, this low supersonic region, is actually quite a dreadful place to be in terms of performance. You get a drag rise there, you get poor installed engine characteristics there, and you get the excuse me, I do have a shocking coarse one, and we also get strong variations in the aerodynamic characteristics and the stability in lift. As you increase in Mach number, it improves, and it's still steadily improving up to Mach 2. But at this point, beyond here, you start running into engine intake difficulties and material difficulties. So we ended up trying to design an aeroplane for Mach 2. Now, what were we trying to do? Well, if you look at the typical mission, you find that only this item, the climb, cruise, and descent, and the en route reserves, are actually predominantly supersonic cases. Everything else is a subsonic flight condition. So you can't ignore at all the subsonic state of the aeroplane. That shows in a way in that this picture over here is the breakdown, the takeoff weight breakdown for a typical mission. And you can see that the fuel, of course, is about half of it. The block fuel is 40%. Quite some of that will be subsonic. Some of these reserves will be 5% of the supersonic fuel. You can also see, although I can't, oh, sorry, that the payload fraction is only about 5% of the takeoff weight, which means it's very sensitive. A 1% increase in structure weight, for example, is a 20% reduction in your payload, and that starts to hurt very quickly. the absolute variation or importance of these variations you can see from this bottom table. Well, I won't dwell on it too much, but by and large, the effect on a supersonic aeroplane is about twice what the same loss would be on a subsonic aeroplane. For example, if you're limited by takeoff weight, then a 1% increase in drag is going to cost you 2.4% payload. I can't read it because there's something else on the screen there, but it's about 5% in supersonics. So the whole thing is actually very sensitive. How did we develop the wing? Well, we started off with a 60-degree, 57-degree delta, which nominally gives you a sonic leading edge at Mach 2. Then we found the extreme tip doesn't do very much, so we cut it off. The next step, which is actually quite important, you see if I can get rid of this. Okay, got rid of it. The next step is actually quite important, is to add a highly swept fillet into the front leading edge at the root. Now that's got several effects. The increased high sweep, if you like, helps in terms of supersonic drag. The increase in lift-in length reduces the wave drag due to lift. Oh, sugar. The lower thickness chord ratio you get on the root, that reduces the zero lift wave drag. And because this works more effectively, oh dear, I'm sorry, gentlemen. Because this works more effectively in supersonic conditions than in subsonic conditions, the aerodynamic center of the wing in supersonic flight is actually moved forward relative to the aerodynamic center in subsonic flight. And we'll see in a minute that that is actually quite important. The other thing it does is that you can fill that up with fuel. So you bring the center of gravity of the fuel forward relative to the low speed aerodynamic center, which enables you to get stability at low speed. The fact that it's a high leading edge sweep intensifies the vortex development and increases the low speed lift, and it actually helps to move the aerodynamic center aft as well. And as I said, the thickness at the root remains high, so you've increased the fuel volume, which is good, and you've also got a chance to reduce the structure weight. Now, that standard of wing actually has quite a strong gradual but progressive pitch-up tendency, and that puts limits on the center of gravity you can use at low speed. The aerodynamic center and the pitch-up is quite a lot infected by the effect of the suction underneath these leading edge vortices and the area which is affected by that suction. So the next step was to crop the tip a little bit and sweep the trailing edge forward, add a little bit more, and that helped to reduce the pitch-up. Now, when you've done all that, and rounded the corners, the planform that you get doesn't look a lot like the original, but that in fact becomes the basis of the successful design. After that, we were really involved in changing the details of this planform in order to minimize the induced drag, amongst other things. Once you've got a planform, of course, you then have to think about the rest of the aeroplane. And here we had a problem. And you have to decide where the nacelles are going to go. You are, in fact, limited to some extent because the length of the engine is the length of the engine. You're stuck with that. Similarly, the length of the nozzle is supplied by the engine manufacturers. The length of the intake really depends on the technology you've got available, but we had it, we knew what we could do or what we thought we could do. And so the total length of the intake is fixed. At the same time, the engine and the nozzle are fairly heavy components. So where you place the whole power plant assembly fore and aft has significant effect on the center of gravity, amongst other things. But then it starts to get tricky. You found that if you had the nacelle too far forward, the corner of the nacelle in particular, there was an interaction between the nacelle and the wing flow field, which gave rise to undesirable characteristics. On the other hand, if you moved it back, you found that you were actually starting to affect the ground clearance limits. That also, of course, excuse me, is affected by the length and position of the undercarriage. Yeah. And that, in turn, is affected by the length of the undercarriage and where you can get it indicated stowed. So where you put the nacelle on the spanwise location affects the undercarriage location, which affects the ground clearance. You also get problems, and we saw them later in life, of course, of possible debris injection with the proximity of the gear to the nacelles. Again, if you move the engines out, you start limiting the outer aileron power. And so the whole darn thing is very much a compromise. And once you've got the compromise fixed, you don't change it very easily. I did mention that we did tests to improve the pitching moment curve. The sort of thing we had at the beginning was this sort of bendy curve. And by changing it, we managed to improve it on the prototype to something more like that, which became, over the years, between 1962, we had that. By the time we finished, we had the aerodynamic center back 3%, and that in that sort of region, which was actually quite important. I think you can see that these changes come from really fairly subtle changes to the wing planform out and to the wing tip. And quite a lot of wind tunnel work went on in order to get that sort of lifting curve change. The result was something like this. The prototype, as I said, is this solid curve. We did make some other changes, which I'll come to in a minute, on the production aircraft, which meant we resulted in something like that, which had a little bit more of a pitch up. But since, in fact, we didn't work to more than about 20 degrees angle of attack, you were never really in the area where the pitch up became a problem. Incidentally, that sort of bendy, pitchy curve there, I think is what is causing Boeing grief on the 800. In terms of the Concorde, when you increase the incidence, or keep on increasing the incidence, especially if you've got any side slip, you find that the vortices, in any case, vortices will break down downstream of the wing. But as you increase incidence on the Delta aircraft, the point at which they break down moves closer and closer to the wing. And when you get side slip on it as well, you can find that above about 18 degrees angle of attack on Concorde, the vortex breaks down on one side of the wing, and you get wing drop. Similarly on the other one, but if you get high enough to about 20, then you just get loss of lift on both of them. So we had to install angle of attack protection, if you like, which meant that above at 17 degrees, we started to get a stick shake. And if you got up to about full 20 degrees, then you actually got a full-blooded wobble on the stick. The reason it was a wobbler was because André Toucard, the French chief test pilot, flatly refused to have anything at all to do with the stick pusher. But nevertheless, Concorde does have some sort of stall protection in that respect. Now, in order to, the next thing you've got to do, of course, is you absolutely must minimize the supersonic drag, or maximize the supersonic lift drag ratio. And to do that, you need, first of all, you need to have a low wing area to keep the friction drag down. You need a low volume in order to get the zero lift wave drag down. You need a long length of the aeroplane, again to reduce the zero lift wave drag. You need a large span to keep the vortex drag down, just like on a subsonic aeroplane. But you also need a long lifting length in order to reduce the wave drag due to lift, all of which, of course, are incompatible in many ways. The friction drag is straightforward. You can just tot up the wetted areas, multiplied by the appropriate skin friction coefficient appropriate to the Mach number, and away you go. And you can't do much about it other than reduce the wetted area. One thing you do have to watch out is you actually have to correct for heat transfer in supersonic flow. On Concorde, the wing area was approximately, the wetted area was approximately 3 times the wing area, and so it becomes a not negligible part of the drag. The volume wave drag, the zero lift wave drag, if you like, depends on the area rule, I suppose, really, but it also depends on the square of the volume divided by the 4th power of the length. So the volume is actually quite an important parameter. In the early days, there was an argument between ourselves in Bristol and the boffins at RE Farnborough. They wanted to have an integrated configuration because it gave a low value of K. Our argument was that a low volume configuration, as we have on Concorde, was actually a better bet, even if it did have a higher than theoretically possible K, we still got a lower drag out of it. The wing then is actually quite thin. It's a maximum of 3%, falling to just under 2, about 1.75% out at the tip there. So the volume to wing area ratio, if you like, is quite an important parameter in terms of keeping the drag down. People have mentioned that we don't seem to have area rule on Concorde. And it's true, we didn't actually waste the fuselage or anything of that sort. But as you can see, the area rule is actually not too bad, even with our unwasted fuselage, if you like. The only thing which comes near using area rule, I think, is where we changed the back end on the production aircraft from the prototype in dotted to the production aeroplane, and that actually improved the area distribution. But we don't have area rule in? No, we don't. But that area rule is not bad at all. We also needed from the prototype, we needed to redesign the wing in order to improve the trim condition and the trim drag. And it was dictated at the time that the only bit of the wing that we could change was the bit outside the production joint at rib 12. And there, so the only bits of the wing we were allowed to change are the hatched areas. And the changes that were made, the prototype wing in plan form is here. And the production wing, we increased reduced the leading edge sweep a little, which actually made it just about sonic on the leading edge. But we also changed the camber, and instead of the rather substantial leading edge droop of the prototype, which was put there incidentally to hopefully improve the subsonic performance, because that gives you forward facing area. And in subsonic conditions, you can get suction on that forward facing area and get the drag reduction. But we had to give that away in order to get the supersonic trim correct. The net result for the Concorde, at least, the breakdown at Mach 2 in terms of drag is that friction doesn't change very much with this span to length ratio of B upon L, and beta is the square root of m squared minus 1. So at Mach 2, Concorde sits about here. At about 1.4, it's down here. So you can see that the biggest contribution, single contribution by far, is the zero lift wave drag. The vortex drag and the drag due to wave drag due to lift are about the same. It changes as down here, where the volume is less important than the vortex drag. Just for interest, I thought I'd put together the changes which we made between the prototype and the production. This is expressed in terms of the Breguet range number, weight times specific range, which is another way of saying it's V times L over D over SFC, which is a measure of the range of the airplane. You can see that most of our improvements actually came from the engine and the nozzle, and I'll turn to those later on. We had an energetic campaign to reduce the parasitic drag, which very largely consisted of going through the detailed design very carefully, sealing off the leaks wherever possible, and where you couldn't, making sure that the leakage actually pointed streamwise backwards rather than across the flow. There was a little bit from the leading edge and the tip, and a bit from that change to the rear body I mentioned. There's also a slightly adverse drag for the change from the prototype nose to the rather more elegant, I think, production nose. But the net result was a substantial improvement in specific range, most of which, as I said, came from the power plant. The one feature that we did have, though I've mentioned trim several times, and that's because on a delta-winged aeroplane, as you go from subsonic flight to supersonic flight, the aerodynamic center moves back. On a delta, it moves back from about 53% back to somewhere near the center of area in supersonic conditions, which is about 2/3. And that is a big shift of aerodynamic center you have to contend with. With our camber changes, we were able to change that so that the aerodynamic center sort of peaks at about Mach 1, but comes forward to about 62% or something at Mach 2. If you didn't have any fuel transfer, then you would still have, even with that aerodynamic center shift and our camber, you would still have a fairly substantial change in trim, and that is a negative elevator angle, which is going to produce an increase in trim. Oh, down. Increase in trim drag. With transfer, we can actually get the center of gravity back from a value which actually gets you stable at subsonic conditions, and it takes you back to about 59% from memory at Mach 2. The result of that is that instead of having this very big change of aircraft trim as you go supersonic, the trim change is actually quite modest and ends up at Mach 2, in fact, with a slightly favorable trim in that the elevator angle to trim is actually nose down. The result in drag is a very substantial reduction in drag because of this, and just for the record, the CMO changes that. To illustrate the fact that you never stop learning about your own aeroplane, it was only yesterday that I discovered that that trim change was actually subject to thermal effects. And if you flew the aircraft in a different atmosphere, different ISO if you like, the thermal effects changed it. And the trim variation with Mach number was quite different. In fact, it happens to be even more favorable. But that was due to the different shape of the wing that you got in this other atmosphere because of the thermal heating effects. That, as I said, was something I only discovered yesterday. The main feature we had to reduce the drag, if you like, was the fuel transfer system. The center of lift I've been talking about is about 6 feet. And if you left the center of gravity where it was, then that's a big pitching moment to change. So the center of gravity is moved back to do that. To do that, we take some some fuel from the forward fuel tanks, and initially it's moved back, part of it into the main tanks as the fuel is used up, but also into a trim tank in the rear of the aeroplane, and where it stays until the end of cruise. At the end of cruise, it's transferred back into the front tanks or into the main tanks again. Now you may think that that is straightforward. In fact, the rate of transfer actually has to be tailored. Oh, okay, because you have to be able to decelerate safely from any point in the acceleration and climb. That means it could be any time. So you actually have to trim your transfer rates in order that you can get back safely. I'll come back to that in a minute. The flight envelope for the aeroplane, defined by several things. Here is defined either by the maximum Mach operating or the maximum temperature operating speed. In this part is defined by maximum operating speed as an airspeed, not the Mach number. In this corner is defined by an aeroelastics limit, a flutter limit, where that is cut back in order that you can maintain the flutter margins actually out here in paper. You have to do it 1.2 times the demonstrated flight speed. Back down in this region, the limit is due to transonic control with hydraulic system failure, which I'll come back to in a minute. Then, of course, you have the max altitude for pressurization and the minimum airspeed, which is standard sort of stall thing. Just for the record, I've put Mach 1 on there so you could see where it is. As I said, you had to match the transfer rate to the CG boundaries, which in themselves had to meet some airworthiness requirements, which were actually new for Concorde. Concorde wasn't certificated to FAR 25, or there wasn't an EASA 25 then, but it wasn't certificated to the 225 rules. It was certificated to a set of peculiar rules that were written for supersonic transports, known as the TSS standards. And they introduced something which I think was introduced into the civil aircraft field for the first time, which was that the flying qualities could be a function of how often you actually ended up in that state. Some people, Sherman and others, will recognize that perhaps as the embryo of the 1309 requirement in terms of systems safety. But what we were told, or what we were told we had to do, was that depending on the probability, the state of the aeroplane, there were certain minimum maneuverability requirements that we had to meet, which depended on, as I say, not only the frequency of occasion, but it also depended on where you were in this region. I should have gone back, if I may. This region inside the solid line was described as the authorized envelope, which means you could fly anywhere inside there at any time. The dotted line on the outside represented what was known as the circumscribed in-flight envelope. And basically the requirements there where you had to have enough variability that you could get back inside the authorized envelope as soon as possible. So that meant that we had some G limits that we had to obey. The occasional limits, which of course were more severe for us, had to be met with one hydraulic system in operation. Now, Concorde had 3 hydraulic systems, but each system fed, it had dual hydraulic jacks, which were normally fed from the green system on one side and the blue system on the other. But they could be fed in an emergency by the standby yellow system, which could be fed to either side of the jack. So in order to get to a half hinge moment situation, you actually had to have 2 hydraulic systems out of the 3 failing, but you could still just get that inside 10 to minus 7 per flight. So what we ended up with, the limits that we found ourselves in the end, again, you may remember this is on a single hydraulic jack. The limits at this end were to be able to pull 1.3 G or 1.2 G at a heavy weight, or at the lighter weight, there was a different problem, but you still had to be able to pull it. At the top, there was a physical limit. We couldn't get further back than that on the airplane anyway. This one was the ability to be able to push over to 0.9 G at VMO. But that's a state, in the transonic state, you really wouldn't want to push over in a state into an increased speed outside the authorized flight envelope under those conditions. The other one, the subsonic one, was actually defined by a stability limit, defined by the elevator angle per G down at about 1 degree per G, I think it was. But the net result of all of that was that we derived a CG envelope, which was a function of Mach number. In order to help the pilot with that, the Concorde Mach meter has an extra function, which you don't see in others. Not only does it indicate the Mach, but there is also a center of gravity indication on it, with the forward and aft range of CG for that particular Mach number indicated, and a pointer which actually tells you where you are inside that range. So in this particular case, the airplane was about there. As I say, that one is peculiar to Concorde. A different situation on control altogether, but one which worried us at the time of the design, was the response to engine failure. Now, when we started out, the only real experience was on the B-58 Hustler, and that had a rather unfortunate history in terms of engine failure. Excuse me. It had what was known as internal compression intakes, I think, but certainly if that engine failed and the intake unstarted, the shock wave was expelled, came out, it affected its neighbor on the same side. Between the two of them, they screwed up the flow over that side of the wing completely. You had a very big yawing moment, a very big rolling moment, and before you knew where you were upside down, which was really not a good prospect when you had 100 passengers on board. So the response to engine failure was quite important to us. In the end, we conquered it, and this is a flight test response to a double engine failure. At this point in time, both engines on the same side were cut. The engine on there. Okay. The aircraft, of course, started to yaw and to slip. The auto rudder would cut in, and about 12 degrees of rudder or something. The side slip was actually limited. This double engine failure was limited to just under 4 degrees, and the maximum bank angle that was produced was about 12 degrees. Sorry, I pointed that out for auto rudder. It should have been bank. So a double engine failure with only 4 degrees of slip and 12 degrees of bank at Mach 2.2 isn't bad. The reason it comes about that way is because of this feature of the power plant. If the engine fails, all the flows are going there, and instead of rushing out and unstarting the intake, some of it goes down there, but most of it is expelled through the dump door, which is automatically opened when the pressure inside here builds up. The spillage of excess air from the engine in that respect produces a lift on the aeroplane, on the dead engine side of the wing, and so instead of the rolling moment due to side slip turning the engine over, as it did on the B-58, with this one, the lift we got from the dump door thing actually killed the rolling moment and actually kept the bank down to sensible angles. Now, if we turn now to the performance side of it, The thrust distribution to the power plant sometimes surprises some people. At takeoff, then you get about a net 12% of thrust from the intake, because in the diffuser, of course, the pressure is actually increasing here on a forward-facing area, so you get a bit of thrust off the intake. Nevertheless, about 82% of thrust comes from the engine, as you might expect, and about 6% from the propelling nozzle. When you get to cruise, however, the situation is quite different. And I should say it depends on the bookkeeping that you adopt. And in this one, certainly the poor old engine has taken all the ram drag. Nevertheless, the front part of the intake in cruise, where the supersonic compression goes on, produces about a 12% drag, if you like. The intake in this part, in the subsonic diffuser, is about 75% of the total. So the intake net is about 63% of the installed thrust. The engine only gets about 8% in that way, and the propelling nozzle actually is 29%. So you can see from that, in terms of supersonic performance, the intake and the nozzle efficiencies are actually the important bits. Now, what I should perhaps mention is that it matters quite a bit. Then the net thrust is a lot lower than the gross thrust which is produced because of the ram drag. So it does mean, though, that if you lose 1% of gross thrust efficiency on either the intake or the nozzle, then the loss in net thrust is about 2.5%. So again, I'm just really saying that the intake efficiency and the nozzle efficiency are the important features. If I start at the front and work back, you may or may not be familiar with supersonic inlets, but they come in various types. The simplest one is what is known as an external compression intake. And in that, what that really means is you can't slow down the supersonic stream except by using shock waves. Now, engines are not able to accept airflow into their compressors at much more than about 0.4 or 0.5 Mach number. So if you're flying at Mach 2, you actually have to decelerate the air that's coming at you from Mach 2 down to Mach 0.5 in order for the engine to take it. You can't do that except through shock waves if the flow is supersonic. So in all these external compression intakes, there's a system of cowl shocks terminating in a normal shock across the inlet, which is the terminal shock. And a normal shock means it's supersonic in front and subsonic behind. So in the diffuser, then we have subsonic flow, and it's obviously a diverging passage. In the supersonic part, you actually have to go the other way, and it's a converging passage. The efficiency that you get depends very much on how you treat those shock waves. The worst one is a simple pitot shock, in which the flow is like this. With the flow, what you get is if the flow is slightly less than you can theoretically get, the shock wave will stand off as a bow wave shock, and the flow even here will be less than 1, and then you get some subsonic spillage around the intake. At Mach 1, you will actually get the normal shock sitting across the front of the intake, as I've said here, and you have supersonic and subsonic. If you go beyond that, then the shock wave tends to move into the diffuser, and that is actually a loss of efficiency. You can increase the efficiency significantly by increasing the number of shocks that you get. For example, the single shock intake would be a 27% loss at Mach 2. If you were to use a two shock intake, you could reduce that to 9%. The same is true, as I'll see later, down around the 1.4 Mach number. The other end, or perhaps extreme, of these supersonic inlets is the internal compression inlet, in which nearly all the compression from supersonic to subsonic flow takes place inside the confines of the intake. Most intakes, in fact, practical ones, are actually known as mixed compression intakes, and which is a bit of each. This, for example, is the flow pattern on the SR-71, and the first shock, this is at Mach 3, not Mach 3.2, the first shock doesn't actually hit the cowl lip, so there is actually some compression outside and some compression inside. Concorde is a mixed compression intake, and it's actually quite a complicated one. There are some important terms we need to understand in this picture. I'm sorry it's complicated, but it's complicated by the presence of these shock waves. The area of the intake is just from the front of the ramp to the cowl lip. That's this solid line. You will find that the not all of that air goes into the intake. Some of it is spilled externally, and so we get external spillage there, and the actual air that goes into the intake is rather less. When you get inside that, you find that some of the air is actually going to go into the bleed and not to the engine, and so the engine actually gets this bit. The Concorde intake starts off with a simple ramp, a 7-degree ramp, and then it's followed by a movable ramp, which is shown linear in this case, but in fact starts off with a 7-degree isentropic compression there, and then a straight bit. That is linked with another ramp back here, so these two move as a pair. Excuse me. The flow is decelerated here and further decelerated by these shocks, and they're all arranged to come together just ahead of the actual cowl lip. The cowl lip itself then, because the flow is still supersonic at this point, and the flow is actually coming on to the cowl lip at that sort of an angle, the cowl lip generates its own shock, which comes up there. It is modified by the fact that at this point there's a change in flow angle, and in a supersonic flow with change of flow angle like that, you actually get an expansion fan around the corner, so the Mach number increases around that corner, and this shock wave actually bends a little bit. You then get inside the intake and over this bleed, you get a region where the Mach number is actually varying from there across the top to bottom, because behind the actual bow shock at this corner, the flow on the bottom of the intake has actually gone to Mach 1. The whole thing doesn't go finally to Mach 1 all the way across until you go actually through this terminal shock. Now, behind that terminal shock, the static pressure is obviously bigger than it was in front of it. You will see illustrations which show the bleed flow going in here, but it can't, because the pressure here is going to be bigger than the static pressure there. That big high pressure will leak into there, and that will stop the flow out there. So the flow enters the bleed flow, in fact, as a discrete jet. Beyond that point, we're into a conventional subsonic diffuser. The dump door I've already mentioned. The dump door also contains inside it an auxiliary blow-in door, because the intake can't supply enough air to the engine and in static conditions or in low speed for takeoff. So we have an auxiliary door which flows in to supply more door to the engine. As I say, it's a complicated beast, but it works. This illustration is the one I've just shown you, and it corresponds to a point, this point, point B, known as the critical point, which is a point at which the total flow to the intake has just reached the maximum. That's where, so the summation of the engine flow and the bleed flow has come to a point where the shock has actually started just touching on the lip, and so you can't get any more flow in there. That's frozen, and from there on in, if the engine tries to take more flow, it has to be at the expense of bleed flow. So the speed velocity in the main duct speeds up. The area of supersonic Mach number there speeds up. This cowl shock changes its shape and moves backwards, and the whole thing moves towards an internal compression intake. Not that it is. At the other end, if the engine flow reduces, then it pushes the shock forward. It increases that gap. It increases the spillage that you get there. This deteriorates into a small sort of set of shocklets. The normal shock disappears, and the bleed inside increases. So you get a situation where it's moving from there to there. The total capture is reducing. The intake recovery is reducing. What you really want to be operating is there, if you can. Now, at this point, I have to digress a little. This is the sort of intake characteristics that you get at Mach 2, and I'd just like to talk about how you actually get this match between intake, between the bleed and the engine. Just digress to this point a moment, which is not an Olympus compressor. It's just one I lifted, just to illustrate the point. This is a plot of compressor pressure ratio against reduced mass flow. That's only the mass flow times the square root of the temperature divided by the pressure. And a constant N1 line at a given inlet temperature, then you find yourself operating on a given N over root T line. That means that you will operate, if the engine is designed to operate along this line, it means you will be operating at a given mass flow, a given W root T upon P. Now, that relates to the intake directly. If you were to take that number for the intake area and divide that by the number for the intake area, you'd get this mass flow ratio epsilon. So that point, if you like, corresponds to one particular value of epsilon. Except that if the engine behavior should shift, and sometimes it does, if it moves towards a higher pressure ratio, so mostly in that direction towards a high RPM, then it's obviously going to demand more flow, so it will actually try to move in that direction, and vice versa if it comes down that way. So that you get, in effect, an operating line, a possible operating line at the given temperature, which varies like that. At the same time, if the temperature varies and the RPM is constant, then you will move along that line anyway, because the N over root theta has changed, and so you'll get different operating lines depending on the outside temperature. So the aircraft has to match those operating lines over a range of temperature. We chose to design the aeroplane for ISO +5, which meant it was operating somewhere in this region. And what you find is these are varying ramp angle, which varies the actual capture. But we also have on there varying values of the bleed airflow. This is 0.04 is the ratio of the choke and bleed area in the wind tunnel to the intake area. But you do get then, as you run along the law we chose, which is that we would run at a constant ramp angle for a while and then run at a constant bleed pressure. As you do that, you find that the bleed from the intake varies, and then at constant bleed pressure it holds more or less constant. The corresponding intake recovery then, if you like, moves up this way, and it's at Mach 2 and ISA plus 5 is just about on the peak of what we can get. The engine itself is a unique beast, really. Its main feature, I think, in terms of supersonic operation is the fact that it runs at a fairly low pressure ratio. And the point about that is when you actually get air entering the engine at a high stagnation temperature, which is what you get when you're at Mach 2. If you by the time you've increased the pressure ratio through the compressors, you've actually increased the temperature of the air quite substantially, gone up from about 127 degrees centigrade to about 560. Now that means, since you actually have a limit on the temperature that you can have at this point, which is the entry into the turbine of 1100 degrees, that actually limits the amount of fuel that you can actually put in, because you can per pound, if you like, because you've only got that margin of temperature rise that you can play with. The reason it changes from Technicolor to black and white at the back is because I grafted another picture of the back end on so that we could include that. The engine, of course, uses reheat for takeoff and reheat for transonic acceleration, but it does use no afterburner for cruise, which is something which no other engine at that time could do. The other point to make on that is that these final nozzle vanes were actually controllable, and we were able to use that to advantage later on. And again, I'll come to that in a minute. The nozzle, again, has to be very efficient. I'll talk to that as I talk about the nozzle. But the Olympus is actually an interesting engine, but it's very specifically, it works at Mach 2. The afterburner, well, you just have to live with it. The nozzle, we changed considerably between prototype and production, accompanied, I have to say, by some rather bitter arguments between the French aircraft designers and the French nozzle designers, but never mind. The prototype nozzle started off with reverser buckets, a straightforward ejector nozzle, but with blow-in doors to like the engine vanes. These were blow-in doors. Thrust reverse was these buckets came across and it was exhausted through this grid or grill. Because of problems with transonic performance, where the engine doesn't normally produce enough pressure ratio to fill this nozzle, so you can get some substantial installation losses in transonic conditions if you got the nozzle wrong. There was a blow-in door here which actually supplied extra air in transonic conditions. You can see the grill in this one, and to be honest, they're not really subsonic designs, are they? There's the blow-in doors just ahead of it there. In the course of the production, we changed from that to the nozzle known as a tuyere reverse ovale, which is the aft reverse nozzle, in which the thrust reverse was actually obtained by a pair of these buckets coming round and shutting, and the supersonic cruise condition, we then had a simple ejector nozzle. There was obviously a bit of a gap there, but it's nothing like what we got from that. And in takeoff or in transonic, subsonic conditions, the ventilation on the nozzle I talked about was obtained by partially deflecting the buckets so we could get ventilation from the inside. A big difference between the two, as you saw from the table earlier. The way the nozzle works is you can have different ways of ejecting bleed. You can just eject it overboard in a choked nozzle, which is one way of doing it, and if you don't get it right, it's not very efficient. You can have a convergent divergent primary, but that needs to be a fully variable one in order to match the thing, and that gets quite weighty and complicated. Or you can have what is known as an ejector nozzle, which is what we used, which is the primary nozzle and a fixed secondary nozzle. Now the way that works, excuse me, the expansion of the jet coming out of the primary is actually, the expansion angle is controlled by the pressure ratio between the primary and the secondary, which is, or the inverse, which is secondary to primary, which is PS to PJ. The subsequent expansion of the primary jet also depends on that ratio. Depending on where this minimum is on the shroud relative to the jet exit, you get a limitation on the secondary flow. At some point you can form a sonic throat, and the area at that throat, along with those conditions, defines how much bleed air you can actually take. Beyond that, the jet expands until it comes down to ambient static pressure at the exit, and that's what you actually really need for maximum efficiency. The main jet, of course, also expands to subsonic pressure just at the exit there, and the conditions that you get depend very much on this pressure and this geometry. Now that is shown in this picture. You can see that if you, if you reduce that pressure, you are more likely to produce a throat on that, and you could even stop the flow entirely if you weren't careful. So increase in PJ goes with a reduce in bleed flow. At the same time, you can change that area, and that will change the relationship. You also find in the midst of all of that lot that the gross thrust nozzle efficiency is changing with this geometry. So you get lines of constant efficiency in there, and where you really want to be operating is up here somewhere in the middle of the best efficiency zone. So how does all that lot go together? Well, if you take the characteristic I just shown you, which is the nozzle characteristic, and overlay it with the intake characteristics, you find that there's a region where the intake efficiency is a maximum and the nozzle efficiency is a maximum. So obviously you try to operate in there, which in this case is about 6 or 7% bleed, something of that sort. There's a limit up here, which is intake stability and buzz, but we never got anywhere near that. So the whole thing is set up to match the two components one to the other. the result is something which is actually quite interesting, and I think quite neat. You get a power plant which is actually self-compensating. Normally, we have an engine flow, a bleed flow. The bleed flow is used to cool the engine bay. Some of it might be taken off. There might be some other bits and pieces poked in there. But at the end of there, this bleed flow is turned into this secondary airflow. So it's slightly higher in temperature, slightly lower in pressure, but it's the same mass flow as you started out there. Then you have the system I just described. If the engine has a hiccup, and engines do, then it will lose its mass. Oh no, I'll start the other way. Just suppose something went wrong and the intake recovery dropped for some reason. The mass flow through the engine would drop. The pressure ratio at the back would fall. Those variable nozzles that I spoke about would actually close in just a little bit. That would increase the area available for secondary flow. So the bleed would increase. If the bleed increases, generally speaking, the intake pressure increases. So a decrease in intake efficiency is compensated by the closed loop effect, if you like. And the same is true if you go through the argument. If the engine has a hiccup, again, the things self-compensate. So you don't have the sensitivity that you do on some of the other designs. And that has helped a lot, frankly. Once you've got all that, you still have to match the intake size to the engine size. Now, most people work with this curve the other way around. This is a function. W root T upon P is the non-dimensional mass function. It's the area, it's the mass flow that you can pass through a given area, basically, as a function of local Mach number. For air, which is what this is, it's a maximum at Mach 1, and that gives you the minimum area for passing a given Mach number. Other than that, a typical engine face Mach number is between 0.4 and 0.5. So if you know the engine face area, you can see it. Well, you know how much mass flow it is, but the engine face area is what you need there. For an intake at takeoff, it's a lot less than that. So usually the engine is sucking at takeoff. At the other end, though, which is where you really want to be interested, the mass flow per unit area is a lot less than the throat. It's also less, generally speaking, at Mach 2, it's less than the intake area you need for engine requirement. So the intake has to be slightly larger than the engine if you're going to match it. The problem is that if you then make an intake, let's say, which matches a particular requirement there for 430, as you fall back in Mach number, the the engine will in fact increase in mass flow slightly, but because of this effect, the intake is able to capture a hell of a lot more. The engine can't take it, so it has to be spilled at the outside of the intake. It can either be spilled, normally it would be spilled as force spillage. The shock here would move, and that flow would simply go around the outside. You can do it by increased bleed, but sometimes it's not possible, and particularly if you actually get to the transonic conditions, it can be quite big. This one, I'm not sure the aeroplane, I think it's an SR-71, but this curve is the inverse of this one. This is the area over the critical area, the Mach 1 area. But it says the same thing, is that the engine demand is such, you can get rid of some of it by overboard bleed, as it says there. You can get some of it by bypass bleed, as we did earlier. But when you get down towards Mach 1, you can get one hell of a lot of spillage, and that means one hell of a lot of drag. So there is always a concern as to how you get the transonic performance out of these intakes. For the record, Concorde sits there. Boom, which is going to fly at Mach 2.2 HOTOL, will actually be worse. Spike 512 at 1.8 would be better. And the Aerion might actually get away with it because it's not all that different at Mach 1.4 to the Mach 1. So Aerion, the spillage could be quite sensible. The other thing we had to do, when we spent a lot of time on it, was making sure that the intake could actually cope with side slip conditions. We had, I think it was from simulator testing, we had some idea as to what the sort of side slip and normal acceleration we'd have to contend with in the case of an engine failure. So we had some target conditions, if you like. Actually, sorting out the side slip turned out to be quite difficult in the end. If you come down to this one, you see that in normal conditions the flow is straight up and down alongside here. But if you get flow off the sidewall, that's in this case is coming off on this side, then the flow can produce a little separation around the lip there, and that in fact can actually spread across. We found that if you actually were to cut back the sidewall in this shape, then that allowed the shock wave to change a little bit, and it allowed a little curvature of flow. So instead of actually producing the shock wave there, we actually got a little bit of extra spillage, and you can see that the results of that in this picture, where we were still found that even though you did that, you had a little separation, quite a big separation actually, in this corner of the intake. And the cure for that was to put a bleed across the cowl in this sort of region and just exhaust it. And that actually improved the recovery. She changes these constant pressure contours, move them outwards. The intake pressure recovery sort of moved. We got 2% on intake recovery back from that. We lost, of course, a little bit of mass flow, about 0.5%, I think, but we got a substantial increase in the distortion characteristic. When you went the other way, when you put flow, if you like, coming across onto this splitter now, the problem there was that that wing, if you look at it the other way, that splitter is acting like a wing. So when the flow comes in from this side, you actually get a higher velocity and lower pressure on this side of the splitter. The higher velocity means a higher Mach number, so that these shock waves on the splitter side would actually converge onto the cowl, and they would produce a sufficiently large adverse pressure gradient to generate some interesting flow conditions in that area. Again, would reduce the worsen the distortion pattern. So again, we found that if you cut back the cowl lip in those conditions, you could actually get back to something pretty close to the original condition, and you could cover side slip in both directions. The net result of all that activity, that was where we started, and that was where we finished in terms of your capability. which I still think is quite an achievement. We spent quite a lot of time juggling with these contours. They actually can be quite important in terms of engine inlet compatibility. This one is called DC60, which is actually the average pressure, if you like, over a 60-degree segment of the compressor face. In flight, we couldn't actually do that because we didn't have the instrumentation. We had 5 inlet guide vanes at the front, so we ended up using a parameter which is closely like, which was actually DC naught, which was just the conditions along any one of these 5 vanes. As I said, we managed to improve the side slip capability quite a lot, and by juggling with the ramps manually, disconnecting the intake control system, we were able to bring the changes on the intake, and so find out what it did to the distortion pattern, as a result of which we could derive intake control laws, which were going to give us the best chance of surge-free operation. The result that we got in terms of side slip, we were looking for sort of capability. The open lines are no surge, the black lines are surge, and so we met our capability. We were also looking at a self-imposed requirement in terms of normal acceleration, and we wanted to get down to 0G. The positive normal acceleration is always less critical, so that wasn't a problem. But again, we pretty much succeeded in terms of getting down to 0G at sort of cruise Mach numbers. We weren't a long way away above it either. The intake control system on the production aircraft was actually a hybrid. We were doing it along the time when digital control systems started becoming popular. We kept the analog control system for the actual actuation of the ramps and the dump door, but we used a digital system to derive the pressures against which these ramps were controlled. So we took total pressure, static pressure, and angle of attack into the system. We produced it. From that, we produced the maximum and minimum ramp angles we could use, and the error that we had between. We were controlling to a pressure in this bay relative to free stream, so we could look at the error and into the drive of the servo valve. We could also, because of the the facility that we had to vary the engine LP speed through using those variable nozzle that I spoke about, we were also able to vary the engine N/root theta limit, which I'll show you in a minute, was actually quite an important feature for us again, because not only did we have to protect against side slipping, of course, we had to protect against Mach overspeeds. We didn't want to have any surge at Mach D if we could avoid it. The way we got around it was, in fact, we used our facility to vary the N/root theta, that's the engine LP RPM limit, as a function of Mach number, and we were able to keep a decent margin between that and the engine surge line. There was one interesting point here, is that this minimum margin is actually defined by a requirement which doesn't appear in the FAR 25 requirements even to this day, although I think that there's some case for doing it. I know at least one instance on a subsonic aeroplane when an incident, not accident, could have been avoided if there'd been a consideration of temperature gradient. But we had to consider not only airspeed changes, but temperature changes, because if you ran into a bit of cold air, for example, the speed of sound will drop. The velocity of the airplane hasn't dropped, and so the Mach number's gone up. And that could be embarrassing. we had to consider a range of them. The worst of them was actually really very severe indeed. It was a change of 21 degrees C in a mile, and that's in a fraction of a second. So, you know, that was an almost instantaneous change of Mach number. But we made it, various fiddles to the intake control system, which I won't go into here, and principally that engine scheduling. We also had some interesting experiments. The diverter on the prototype actually didn't work all that well. The flow separated and came out, and it was actually draggy. So we found that out by doing some flow visualization in flight. We made up a mixture of paraffin and some other oil and lamp black, painted that onto the white painted airplane, went off and flew it. When it got to the high temperature, which went to Mach 2, the mixture became sort of fluid. It flowed, took up its new pattern, and then you slowed down, cooled the airplane, and it was frozen for you to see. But as you can see, the production or pre-production aircraft, we got the diverter sorted. One other thing we found right at the last minute was that we could actually get a really important, as it happened, increase in specific range by changing the geometry of this car lip. This was the original. We actually thinned it a bit and dropped it, and that actually reduced the external drag, changed the intake recovery a little bit also. We got an improvement of 130 miles in WSR, which may not sound much, but it happened to be the difference between being able to operate into Washington with reliable reserves and not. So it was actually quite important. Now then, on the negative side of the thing, the operation of Concorde in the end, as we all know, was limited by overland sonic booms. I think I am perhaps the only person in this gathering who has first-hand experience of primary and secondary sonic booms. The primary sonic boom, I think, fairly familiar. The airplane generates some complicated shock waves at front and back. By the time they get to the ground, they've actually mutated into an N wave. And here we have the sort of responses on the ground you get for various aeroplanes. This is the shuttle at very high altitude and somewhat lower altitude. Concorde is actually quite steep. The Blackbird, flying a lot higher than Concorde, is actually quite low. And the F-104 is also quite, but it's short. The secondary boom, so-called, actually comes from a reflection of the first primary boom off the ground. It goes up to about, well, in some cases either 500 kilometers, where there's a combination of temperature gradient and wind, which actually refracts it, sends it back down, and it could bounce again, or it could even get up to 100 kilometers and then bounce back down. Now, with respect to my own personal experience, the first one took place here in the early days before Concorde even flew, where we were camping on the west coast of France, and just walking along, strolling around with a glass of wine in my hand one day at lunchtime. There's an enormous bang bang, and I nearly spilt the wine. I got back to work and asked one of the French guys who might know what sort of intensity it was. He said it'd probably be about 1 pound per square foot, because they had a flight test range off the end there. Fast forward several years, and we were in a sailboat going from Plymouth to the Channel Islands, and we were about here, 3 of us on board. Bob McKinley and myself are both Concorde veterans. We were on watch, and Paul was actually sleeping down below. All the sound that we had, of course, was the sound of waves lapping gently on the hull of the boat. And all of a sudden, a boom, boom. Well, Bob looked at each other and said, "Concorde." Paul came rushing out of the cabin and said, "What was that? Has the mast fallen down?" So we reassured him, and no, okay, he went back down. A couple of days later, we were actually sailing back from here back towards Plymouth, and damn me, the same thing happened again with the same bloke down below. And this time he came out and said, "That was Concorde, wasn't it?" I don't know quite what to make of that, but I'll come back in a minute. The secondary booms actually took place I experienced them in this very house. Actually, we were sitting down watching television one quiet autumn night, and all of a sudden all the windows and doors in the house rattled for about 2 seconds. At that time I was able to tell my wife what it was, because by that time I was sort of chief development engineer on Concorde, so from our point of view it didn't matter. But it had started with complaints, public complaints from people in this area about this rattle, which happened to coincide with the time that Concorde was flying over there. Now that was actually somewhat surprising, because Concorde had to decelerate back here over Ireland somewhere. So eventually we worked out it was the secondary boom. In terms of public reaction, I don't know whether it was fortunate or unfortunate, but the British government decided that they would actually, without walking too much, or arguing too much, they would actually pay compensation for any claimed damage. You'd be amazed how many people store aquariums with exotic fish directly above an expensive television set. But they paid it, and there you go. I don't know quite what to make of that. There's always going to be somebody in an area that are going to complain of that sort of disturbance. We are talking about flying supersonic over land. The north of England have got a saying that there's naught so queer as folk, and I think that might apply here. I'll talk about it a bit later, but that was my own experience on it. I think it was acceptable to me because I knew what it was, because it was a once-off. If I didn't know that, and it was repeated fairly often, I think I might have a different point of view. I did, as a matter of interest, wonder how the sonic boom overpressure that I'm used to dealing with compares with the parameter which NASA are now suggesting we use, which is sonic boom loudness, and in particular how the claims of 75 dB stack up against what I knew. It turned out that the thing is actually quite critically dependent on the rise time of the booms, and also dependent on where you are. If you're outdoors, you get a quite different level to if you're indoors with the windows closed, for example. I found that 1.5 pounds per square foot, in fact, which is claimed as a 75 dB loudness. Actually, that depends on you being indoors with the windows shut. If you happen to be outdoors, then it's 95 dB, which is a very different kettle of fish. It doesn't help very much to just have these lines, which we just calculated incidentally, just using a couple of NASA reports, which are fairly standard methods. But you need to know where the aeroplane is in order to make a judgment as to what the noise level is. So this was done for a 50-passenger aeroplane, just for curiosity, no other reason. And I overlaid on it the typical Concorde climb path, because that you need, as I say, you need to know where you are in order to understand it. And it turns out, of course, that to look at noise levels at the end of cruise is not actually going to help you very much in terms of public reaction, because the bigger noise levels are down here in the transonic acceleration phase, where the aircraft is lower, which is the primary reason for it. Um, and the thing is actually quite sensitive. In this particular case, Concorde was going, this aeroplane was going through Mach 1 at about 30,000 feet. And you get generating a boom of just over 2. If it had gone through at 25,000 feet, it would have been a boom of 3.5. And instead of a noise level of 83, it would have been 87 or 88. So when you're talking about loudness and its acceptability to the public, I think you have to be rather careful about specifying the conditions under which you are describing the result. It'd be interesting to see what the Quest results come out in that respect. Okay, the other bête noire for Concorde was airfield noise. We set out to be no noisier than the then current jets, but of course we were. Concorde was still fairly heavy. In the intervening years, the noise has come down. The jet noise has come down considerably. Today we are working down in this area. The only reason Concorde got into New York was because the aircraft handling was so good that we could convince the authorities that we could do what could only really be described as a split-arse turn immediately after takeoff. What we had was the principal runway taken off here, and the Port of New York measuring point there. Had we flown over it, we'd have rung the bell every time. So the aeroplane would take off and do a sharp turn and away, which was in that. I must admit, the first time I saw it was they were practicing it in Casablanca, and I wondered what the hell they were doing. But the noise airfield noise was and is a problem for supersonic transports. The regulations have changed to go with it. We no longer orbit up there. Concorde was up here, but we're now talking about noise levels down in this region. There is a twist to it, which I'll mention now because I think it's quite interesting. The latest regulations, which FAA are just putting out in NPRM, relate to a change in the standard in between aeroplanes certificated before or after this December 2017 and 2020. Now it happens that if you have an aeroplane which is less than 121,000 pounds takeoff weight, and you apply for its certification before the end of next year, then you won't actually have to apply stage 5 regulations. You can get away with stage 4, which means that you actually won yourself a margin of 7 dB on the cumulative noise level, not to be sneezed at. I think there's at least one aeroplane, what we're talking about, which might be in that state. Right, look into the future a little bit. Sonic boom, we have NASA's Quest program, which is progressing well. They are, as I understand it, they are trying to reduce the noise nuisance by modifying the characteristics of the sonic boom to spread the rise time over a longer time, and in fact to reduce it. As I said earlier, I think they will also look at that secondary boom noise. As I said a bit earlier, I think we have to be careful how we interpret that, because people vary differently. I haven't really got much to say on that because it's a research aircraft, but I would just comment that they obviously can't see over the end to land the aeroplane, and so they are proposing to use closed circuit TV as a display, as are a couple of other aeroplanes, I believe. That's fine. I hesitate because although that might be great with a test pilot landing in daylight in at Edwards, I'm not too sure how it would pan out with another pilot landing on a short runway biz jet on a dark and dirty night with a crosswind. But we'll only see. But I said that's my prejudice, nothing more than that. Time will tell. Boom is perhaps the most publicized of them. Is meant to be a 2.2 aeroplane with a range of 4,500 miles. Its main problem, as far as I can see, is there aren't any engines for it. And there may not be any engines for it. And I'd like to explain why I think that. Oh, beg your pardon. I think these bifurcated intakes, particularly when you think of side slip, you have different intake conditions coming to the engine from one side or the other, and that's going to change the distortion pattern. Lord knows what that will do, but as I said, they haven't got an engine to try it on. The XB1 has been tested with a Concorde-like intake, but it's a different aspect ratio. Concorde would be wider. It may be the camera angle, but that looks to me like quite a steep cowl angle, which might mean there'd be more drag and more intake compression. But again, they can't design the intake until they've got an engine. What might they have problem with the engine? Well, again, this is a personal view, and somebody may come back and tell me you got nonsense. As you increase in Mach number, the entry temperature at the front of the compressor face is going to increase steadily. It's further going to increase as it goes through the compressor. And so, as on the Olympus, you'll find that the compressor delivery temperature, this is in K, by the way, not in C, is a point. You then have a limit on turbine entry temperature from materials. So there's a margin, a temperature margin, if you like, which represents the amount of energy that you can put in without exceeding the TET limit. Now that energy has got to be used in the first place to drive the compressors, and whatever's left has got to be used, or is used, to give thrust. Now, I know when you look at the SR-71, which had a very low compression ratio, my analysis of it showed that when you got to 3.1, that temperature difference you had, that margin, was only just enough to drive the compressors. You really didn't get any thrust at 3.1 out off the J85, except what you got from the afterburner. Now, when I come back to today's engines, to LEAP, for example, it's running at a very high pressure ratio, but the temperature, the TET limit is also increased dramatically. So there's actually quite a big margin there. What I don't know, what I worry about, is if you take CFM56 core or something and you take it up to 2.2, which is what they're proposing, then how much of that margin is needed to drive the compressors, bearing in mind that instead of running that compression ratio of 11.5 to 1, they're running 30, 40, maybe 50 to 1. So I don't know, but I do wonder whether there's enough margin in the current technology to sustain non-afterburner thrust at 2.2. The other point that worries me is similar. If you take a bypass engine, the thrust you get is the mass flow through the fan times the difference between the fan exit velocity and the entry velocity, plus the core flow times the same thing. Now, at Mach 2.2, which is where they're talking flying, V0 is 2100 feet a second. At 1.4, it's 1350. Now, just looking at that equation, if you're going to get any cruise thrust, the engine exit velocity has got to be bigger than that. Now, presumably, for the same engine cycle, the takeoff jet velocities will reflect the relative numbers that you have to have for cruise. Concorde jet velocity, just for the record, is about 2600, and I'm guessing the affinity is maybe about 900. Now, the jet noise is proportional to the 8th power of that velocity difference in one region, about the 5th power when you get to the top. So the GE engine, they say, conforms with stage 5 noise regulations, and it got enough margin to cruise at 1.4 Mach number. But if you're going to fly at 2.2 Mach number, then you'll have to increase the jet velocity by 40% or something. Now, if that does apply for takeoff, and I don't know whether they've got some technology that will do it, then if it does apply, then you're going to have considerably more noise out of an engine designed for Mach 2.2 than you are for one designed for Mach 1.4. And I think it will probably be enough that you might not even be able to meet stage 4 noise levels of a Mach 2.2 engine. And I think the higher the cruise speed, the more difficult that's going to get. Again, I stand open to correction on that lot, but that's where I think I am at the moment. Another feature of the boom design, and it's a feature of other airplanes as well, is that they produce these marvelous look out of the windows. Well, that's a market man's dream and a designer's nightmare, because it'll be designed to FAR 25, which has got requirements relating to sudden depressurization, and which is why Concorde's windows are actually quite small, because it has to meet a depressurization requirement. There's no way that size of window and those number of windows is actually going to meet that. So they may have a bit of a shock coming. Spike, I've got mixed feelings about Spike. On the one hand, it's got a platform like that one that NASA designed in the 70s, the Arrow wing, which had quite a good lift-drag ratio. NASA were getting about 10 or 10.5 at Mach 2 or 2.2 out of their Arrow wing. But of course, you won't get that on a bizjet, because the thing doesn't scale. You can scale the wing down, but the fuselage is actually limited by the size of human beings. And so the fuselage wing area, or volume to wing, wing area is bound to be bigger on a business jet than it is on the 300-seater that NASA were talking about. They claim laminar flow on the wing. I doubt it very much. We'll see in a minute that Aerion say that to get laminar flow, you have to minimize crosswise flow. A feature of swept wings is crosswise flow. I don't see it happening. I think it's something they've written down and hoping it's going to be right. The other thing they mention is full span leading edge and trailing edge flaps. I don't see how, because when you deflect the trailing edge flap, you produce a nose down pitching moment, and that has to be trimmed out by a tail change if you've got a tail. How are they going to trim this out on this one? The only possibility they've got is to use these outer wing controls as trims, but first of all, they're highly swept, so they're not very effective. And B, their moment arm is not all that different to the moment arm and the flaps they're trying to trim. So I just don't believe that bit. I don't see in the illustrations, I don't see much evidence of an area-ruled fuselage, and that's shaped and located to maximize favorable interference. I'm not sure how that might work. It might, but it might not. And again, of course, there aren't any engines identified suitable for Mach 1.8 yet. To fly at Mach 1.8, you would need a variable geometry intake and some sort of intake control system. And there's no indication of that in the published data. And those nacelles look awfully short to include an engine, a nozzle, and a variable geometry intake. And there's no sign of a spike or anything. The other thing is that their numbers just don't add up. you could do a very simple sum, as I did, if you take the empty weight and plus the weight of the passengers, a lift drag ratio of 9, say, and installed SFC, you get a VL/D of SFC at 1.6 Mach number, which is what they say they're going to do long range, rate 450, and with a takeoff weight of 115,000, that gives you a Breguet range of 6,900. Okay, but 115,000 with those weights means 64,150 pounds of fuel, and they've said the tankage is only 56,000. That would drop anyway to about 5,000 when you take normal reserves into account, so the numbers don't add up. The alternative is just to take that with the fuel, and then you get a takeoff weight of 10650. That would knock the practical range down to about 4,500, which is a hell of a lot less than the 6,200 they're claiming. Unless they're claiming a Breguet range, but you can't fly that anyway. My own guess is that that empty weight is far too low. You compare it with the Gulfstream 5, which is 1,000 pounds less, and 90,000 pounds instead of 115,000 pounds takeoff weight claims. Aerion is an interesting airplane. It's gone further than most of them. It's actually got an engine proposed for it, which is a big start. I thought I'd just show you a 1954 proposal for a supersonic transport, which is not all that different apart from where the engines are, is it? The main feature of the aeroplane is it claims a natural laminar flow wing. Now, I can see the principle, and there's a lot of clever aerodynamics gone into the thing, so why am I still uneasy? Well, the principle seems to be that instead of having the pressure gradient on the top surface as you do on a normal wing, which is that where you get an adverse pressure gradient, which doesn't help boundary layer stability. The proposal is that you shape the wing so that in supersonic conditions, you actually have the pressure dropping all the way back along the surface. So you have a favorable pressure gradient, which promotes natural laminar flow. Fine. And if you look at this picture, you see they've got, this is lower pressure at this end, the high pressure there. So yes, they have got a favorable pressure gradient going all the way. They also say that in order to maintain that, you actually have to control the span-wise flow, and so you're also dependent on some aerial in some clever design there, which actually controls the flow of the top surface of the wing. My concerns are that they may or may not have taken into account the fact that from the intakes they've chosen, at Mach 1.4, there will be a shock from the cowl, and that will go back across there. So at least on that, in that part of the wing, the outer part of the wing, there will be a substantial adverse pressure gradient as you go through the shock wave. And so I can't see how you can maintain, say you're going to maintain laminar flow over that part of the wing. If you went to a higher Mach number 1.6, it would be an even bigger part of the wing which would be subject to that. The other point is that they make the point in the patent, which incidentally is a very good description of what they're thinking. They go to the point that the geometry of that leading edge is actually quite important. And I think what worries me there is if that gets damaged, gets bumped. There's always the problem with flies, of course, but laminar flow is always fallen down on the practical side rather than the theoretical side, and I'm not sure that this is going to be different. The wing is, of course, very thin, but it's no thinner than the Concorde, so but it doesn't leave much room for any flaps other than a simple flap. And there's no indication of any actuation. There's bound to be some compromise there as well. So it's all going to knock it down. Yes, in theory, you get a 65% reduction in the skin friction coefficient. But hang on a minute. The total skin friction, when we looked at the curve much earlier, the total skin friction might be in this case about 40% of the total cruise drag. The wing wetted area is only 50% of the total wetted area, and the gain from this might be about that's about 35% of that. So you might gain 65% of this of the wing skin friction. So the gain, aircraft gain you're looking at as a maximum is 65 times 50 times 40 is 13%. It's that, and then the uncertainties which go with that, and that leave me wondering a little bit. The intakes, as far as I can tell from the illustrations, are simple pitot intakes. Okay, that you don't need variable geometry for a 1.4 Mach number, I agree with there. Although you might if you wanted to fly at 1.6. What I am surprised by is that they've left it as a simple pitot intake and nothing else, because that will give an efficiency of about 94% at Mach 1.4, which is where they say they're cruising. And to somebody building Concorde, 4% loss of intake efficiency, which at Mach 1.4 translates to it could be about a 5% increase in intake efficiency if you put a spike in, and that with 1.4 would translate into a 7% increase in thrust. Believe me, thrust is at a premium. As I said earlier, you've got no spillage control. I'm wondering about the possible nacelle to fuselage interference drag. There have been cases where nacelles quite close to fuselages, particularly where there's any fuselage taper, can give rise to drag. I'm sure they'll have covered it, but it's something that if I were asking questions, I would ask. The engine is perhaps the good point of their proposal. Development of the CFM56. As it says on the advert, it doesn't need variable geometry. They've chosen to use a plug nozzle, which I'll come back to in a minute. They have a sensible bypass ratio of about 3 to 1, so that it goes there. They are saying the cruise consumption above the CFM56. It looks to me as if the takeoff jet velocity might be around 860, 900 feet a second. So yes, it probably is an engine here that's going to give enough thrust and a sensible SFC at Mach 1.4 and still have a fighting chance of keeping the noise levels at takeoff. For the nozzle, they've actually chosen a plug nozzle. You can see the spike coming out there. For those of you who don't know it, that means a variable spike which is moved up and down relative to the jet pipe, which changes the area of the exhaust with Mach number. They've actually added a very convoluted exit to the core there, which is obviously intended to get better mixing and get the noise down. If I compare the proposals with the Concorde, basically all of them have actually got more wetted area to wing area. So the zero lift drag coefficient, the skin friction drag coefficient, is actually going to be bigger just on that count. They also, for the region I mentioned earlier, have a much bigger maximum cross section to wing area. So the zero lift wave drag is going to be bigger than Concorde also. Some of this is a bit speculative, gentlemen. but the estimate I make of the various aeroplanes is that they all give a better range than Concorde. That's fine, and they'll all be lower noise, of course. I didn't correct that one. That's still an impossible tankage on that, and I think that might well be down to 4,500 rather than 4,950 at the end of the day. But yeah, they're interesting. I think there are some questions needed to be answered, and I think I've run out of time otherwise. I'll leave those there. There are some interesting references there if you want to follow up. Thank you very much for listening.
Hey, Clive, I don't know if you have any. We have a little bit of time for questions, possibly. I know that some people are running.
Sorry?
Can you hear me?
Yes, I can hear you.
All right. Now, did we have any questions in the room here before we go on? I know there's a lot of people tuned in. All right, I'm going to sign off on my end, and then some of the people, I know there's a lot of people listening, so they can go ahead and start asking questions, I guess taking turns, maybe putting up on the chat.
Have I baffled them or bored them?
I think it's
this is very, very interesting. We appreciate it.
Okay, any questions? Good.
I think that there might be some. Let's see. I know we have people from some of the OEMs that have logged in, and maybe some of the NASA people. I know there's an FAA group as well.
So there's no questions from Moses Lake. Thank you very much, Clive. That was really interesting. If it's possible to get a copy of the presentation, Shem, that would be wonderful.
Hopefully it worked. It said it's recording, so I should have one available.
Well, if the worst comes to the worst, Shem, I'll send you a copy of the PowerPoint.
And we would appreciate that too.
Anything from Gulfstream? I don't know if anyone's going to try to tune in. And then we have NASA and the FAA, Bombardier.
So this is Steve Edgar with the FAA. I just wanted to thank Clive for the presentation. It was very, very informative, and we would appreciate having copies of the slides as well.
Okay, thank you.
Maybe try. We tied in here.
Anyone else?
This is Brian Lee from Boeing. Clive, it's nice to see you again.
Hi, Brian.
And thank you very much for putting this all together and taking the time to present it. It's really fascinating stuff.
Oh, good. I'm glad it was interesting.
All right, looks like it's all quiet on this end. I don't know if anyone from, I know there's Gulfstream and Bombardier and a couple other entities out there.
We're not sure. We never.
Hello from Gulfstream. Can you hear us?
Yeah. Yes, I can hear you.
Okay, good. Question, I wonder if you would comment on your perception of the commercial success of the Concorde, and if there's one thing that, looking back, that might have improved its commercial success.
Yeah. I think I'd almost like to beg notice of that one. I think the price of fuel didn't help. That was for sure. The accident, of course, was the just put the mockers on it really. But I think it wouldn't have gone on much further because I think the airlines were finding it difficult to maintain the avionics, especially. It was 1960 avionics, and I think some of the motherboards had been soldered beyond all recognition. What actually stopped it selling in the first place? Do you know? I'm not sure. Can I take a rain check on that one?
Can I ask a follow-on then? Given all of your personal studies of the current competitors for a commercial supersonic aircraft, what would you say are the odds that one will be offered for sale in the next decade?
50-50. And I think it'll be a 1.4 Mach design. Does that answer?
Yes, thank you very much.
I really think the quest for equaling Concorde speeds is actually going, in my view, is futile, because I don't think the engine physics will let you actually meet the cruise thrust requirements and the noise requirements at the same time. As I say, at the moment, my feeling is that you can just about manage it at 1.4 Mach number. I'm not sure that the present Aeron design, which with its laminar flow, will necessarily come up to the promises which are made. But I'm fairly happy. I think that somewhere in the middle there's a 1.4 Mach number design that can be made. Whether it's economic, that's another question. I mean, I didn't say it, but one of the things that crossed my mind when I looked at the Aeron GA compared with Concorde is there's an aeroplane which is what, 80% as long as Concorde, and it carries 10 people instead of 100. Yuck. We did.
Hi, Clive. This is Jeff Schrader from the FAA.
Hi.
That was a great presentation. I was just curious if you've ever spent any time studying the oblique wing design, which I believe was also a Mach 1.4 cruise.
Personally, I haven't. I don't. If I wanted to know anything about it, I'd probably go to Island Cruise paper that he wrote in Stanford. I think he's got a paper called Unconventional Configurations or something of that sort. But no, I've never studied the oblique wing.
Okay, thanks.
Oh, I would just remark, of course, that the oblique wing, by definition, carries one wing swept forward, and so you've always got the old-fashioned problems of aeroelastic divergence on one half of the wing. Could be interesting.
Yeah, one thing I remember when they were doing some of the more detailed design studies is it also suffered from some potential meeting the evacuation requirements.
Uh-huh.
There's always something.
There's always something. And it's never what you think it's going to be. Well, there you go, Shem.
Yeah, I think that it would probably have gotten all the questions that people are ready to ask anyway. We may get some over email, so I can forward you some if you like.
Yeah, that's okay.
And with that, I guess thank you everybody for tuning in, and we'll get any papers. I'll try to get a copy of the presentation as well, and we'll just try to tune in next time. We're going to try to do it again with some other people. If anyone, a few of you that are listening are interested in doing a presentation like this, I know Jeff, Chuck, Tom, I think you're listening, and some of the other people. Brian Lee, of course.
Well,
it would be really excellent.
If you do that, Shem, don't forget to invite me.
Oh, you definitely would be. And you
Okay.
could be on the question, asking the questions then. All right. Well, thanks.
Okay.
I'll go ahead and shut it down, and thank you for your time.
Okay, Shem.
And we'll see you. I'll
Take care.
have to get out there and see you.
Excellent presentation.
Whatever we do with WebEx, there's always somebody in the background with their phone on.